Hi, welcome to another video. In this video, we're going to discuss domain and how to find it for functions that are defined over real numbers. So let's get right to it. The last video, we sort of explored domain a little bit. I gave you a definition for it. We looked at what we can have for inputs that give us a real numbered output. Now, right now, when we say that, a real numbered output, we can have functions that have outputs that are imaginary numbers or complex numbers defined over the complex. But for things that we normally graph, we're going to restrict this to functions that are defined over real numbers. And that gives us a pretty clear definition of what domain means. So let's check it out. What the domain is for us is the set of inputs of a function, so these numbers that I can plug in, that give us a real number output, something that's not imaginary and something that is defined, so not the function divided by 0. And that the function can handle. And that's later in the class when we talk about some functions that can't handle like negative numbers. So we're going to discuss that today. We're going to look for the two main problem areas that we're going to focus on, and then there's a third one that we get down the road. So when we talk about domain, you got to keep that in your head. So the set of inputs that give us a defined real number output for a function. And there's two problem areas that we really look at. Now, down the road, when we start talking about logarithms, and we're not quite there yet, we'll get there in a little while. Logarithms are going to add one more sort of problem area that we have to consider. It's not really a problem, it's just something that we have to consider, that hey, there's some numbers that I am not able to plug into logarithms. There's also some numbers that I can't plug into square roots, or in general, even roots or denominators. So when we think about square roots and denominators, something in our head's got to be like, yeah, we might have some issues with these things. So let's explore those today. We'll look at a few examples on how to find domain, what to be thinking about, and what not to get confused on. So again, one more time, we got this thing called domain. It's a set of inputs that give us a real number output for a function. And for now, there's two areas that we will look for. Later on, we'll add logarithms to this, but for right now, we're going to really be concerned about square roots, and we're going to be concerned about denominators of fractions. So in square roots, if you remember this, when you have a square root, it can be 0. That's what we explored in the last video when we evaluated and said, hey, can you plug in some number that gives you 0 inside of a square root? Yes, that's fine. Can you plug in some number that creates the inside negative? The answer is no. So when we see a square root, in our head we think the inside has to be positive. It's a really optimistic function. It's all going to be positive. What that means is if we plug in numbers that make the inside, the radicand of our square root, that make that negative, those are problem numbers. So what I always like to tell students is that a square root is going to tell you what it wants to have. So it's going to give you this range of numbers, this interval of numbers, this domain of what numbers it wants to have. A denominator, when we think about that, a denominator just says what it can't have. It can't have numbers that make the denominator equal to 0. So when we're filling this out, square roots, the inside must be positive. It's telling you what numbers it wants to have. It says, give me these numbers so I can maintain my positive inside. Denominators, well, they're not about positive. We can have fractions that are positive or negative or 0 on the numerator. There's only one thing that we worry about with fractions. It's that the denominator cannot be equal to 0. And if we keep that in mind, we'll have a much better shot of finding domain. Right now, I just need to warn you that students get these things confused a lot because they see it a couple times, but they never really understand why it is that you need these cases met, and therefore they confuse us. And they see square roots and they go, oh man, I gotta set that equal to 0 and then solve it. No, that's not what we're talking about. Or they'll see a denominator and say, oh, I need that positive. Why? That doesn't make sense. So let's understand really what is going on here. When you have a square root, if you end up with a negative inside of that square root, that's going to be an imaginary number. And since we are talking about functions over real numbers, that's a problem for us. So how do we avoid real numbers? Is it by making it equal to 0? Well, no. How we avoid imaginary numbers and complex numbers how we avoid that and stick with real numbers is that we find numbers that when we plug it into the square root, It keeps the inside of the square root 0 or more. In other words, positive and 0. So what we're going to do is we're going to take a look at our square root and say, okay, that's a function. I'm looking for the inputs that give us a real number output. I'm going to say, I couldn't give a rip if this thing equals 0. That's fine. Having a square root equal 0 is okay. So if we plugged in, let's see, like 5/4, and we'd have 5 minus 4 times 5/4 would be 5 minus 5 and give you 0, that's totally fine. But we can also have numbers that make it positive. So we're not looking at the idea that let's set it equal to 0. We're really thinking about what a square root needs to have. What a square root needs to have, it needs any numbers that are going to keep this positive. And so how we find it is really we take the inside of the square root and we let it be what it wants to be. The inside of your square root, it wants to be positive. It wants to be greater than 0. Greater than 0 in math is the way that we say positive. We also know that we can have numbers that let it equal 0. So in general, we set the inside of our square root greater than or equal to 0. Please don't ever set this thing equal to 0 and solve it. You're confusing a denominator idea with a square root idea. Now, some teachers might have taught you to do that and say, well, then you got to go back and make it an inequality. That's really bad form because sometimes when we divide by negatives, our inequality has to change, and I've seen a lot of students miss that. So, long story made real short, there's two problem areas. There's square roots and there's denominators for now. Later on, we're going to add logarithms to that list of domain issues we've got to deal with. So for square roots, we're trying to tell the domain what it needs to be to keep the inside of the square root positive. To find that, we say, well, what does the inside want to be? The inside wants to be greater than or equal to 0. The inside wants to be positive. Let's find the range or interval of numbers that does that. I mentioned to you in the first couple videos that part of this series is reviewing some concepts that we often forget. One thing we often forget is that when we're solving inequalities, there's one time when you have to reverse the inequality. It's not when you add or subtract. It's not when you get a negative. It's when you multiply or divide by, not even when you multiply or divide, just when you multiply or divide by a negative number. So when we're solving this, and we subtract 5 and get a negative 5, that's totally fine. We get a negative 4x greater than or equal to negative 5. There's no reason for us to reverse that inequality. But as soon as we divide by that negative, no matter what we get over here, when we divide by a negative, that action reverses our inequality. So greater than or equal to becomes less than or equal to. Notice something real quick. If this had not been a negative, we would not reverse that inequality. Even though we're getting a negative on the right-hand side, that does not matter. So dividing by the negative or multiplying by the negative, which we see much more rarely. We don't really see that a lot because of the way that we structure solving equations. But if we divide by a negative, negative 4 divided by negative 4 is x. Negative 5 divided by negative 4 is positive 5/4. But because we divided by a negative, notice we can get a positive number, we are going to reverse that inequality. And here's what this says to you. If you really think about it, internalize what's going on right now, the square root wants to be positive. The inside wants to be positive or greater than or equal to 0. So we say, let's give it what it wants. Let's let it be greater than or equal to 0. Let's solve it. And when we solve it, it says, as long as you meet this condition right here, you're going to have numbers inside your square root that are positive. That's what we want. So with a square root, maybe this makes more sense right now. A square root tells you what it wants to have. A denominator is going to tell us what it can't have. So it's a different logic there. And when we say, hey, the domain is this, there's a few ways to write it. Before we go any further, I want to make sure that you understand one more thing about this. Notice that there are a lot of negative numbers that satisfy this. So x is less than 5/4. That means like, 1.25 and less than that. So 1 would be a valid number here. 0 is fine. You plug in 0, you get square root of 5. That's totally fine. When you plug in 1, you get 1. Square root of 1 is 1. When you plug in negative 1, well, 5 minus negative 4 would be 9. Square root of 9 is 3. So negative numbers are fine to plug in. Notice that we saw last video too, that you can plug in negatives into a square root. That's okay, as long as the result that you get inside of it is positive or at least 0. So this includes a lot of negative numbers. That's not the point of square roots. You don't say, oh, I plug in positives. Sometimes that doesn't work. Like if we plug in 10. 10 is a positive number, but 5 minus 20, well, that's negative 15. Sorry, that would be 40. 5 minus 40, that's negative 35. Square root of negative 35 is an imaginary number. We can't have that. Square roots tell you what it wants to be. So it wants to be positive. We solve it. And then this right here is the interval of numbers that are going to give you a real number output for that function. So we go, yeah, it wants to be this, solve it down. That's going to give you real numbers. And that's exactly what the domain is for us. The two ways to write this are, you can write it like this, but more appropriate than that, it's set builder notation. It says, I'm going to tell you that the set of numbers that works in my function, or that the inputs will give you a real number output, are based on the independent variable x. That vertical line is pronounced such that. So x such that x is less than or equal to 5/4. And this right here gives you a set of numbers that works as inputs. Do you see it? Do you see it says, hey, if you replace your x such that x is anything in this range of numbers, so less than or equal to 5/4, it's going to be a positive number. And we know that square roots of positive numbers are a-okay. Those are all real numbers. That's what we're talking about. The other way that we can write this is with interval notation. Interval notation is where we use those brackets and the parentheses. We say, well, you know what? If I had an interval of numbers with 5/4, it says x is less than that 5/4. That's this way. Because it has that equals, I include the number 5/4 with a bracket. And this says any number between negative infinity, that's way over here, to 5/4 will be an input that's going to give me a real number output. We always use parentheses for infinities because you can't actually attain that number. We always have these in order from left to right, just like a number line is. So we start small number and big number. Even if this is reverse going that way, we'd start at 5/4 and end at positive infinity. The equal sign determines whether we have a bracket or not. That's got to make sense right now. So inputs, me and our domain, we want square roots to be positive. We solve it down, and there's two ways to write that domain. The next one. So that doesn't have any square roots, but it certainly has a denominator. This is the other place that we look. We know that denominators can never have 0 on the bottom of our fractions can never have 0 in the denominator. We can't ever divide by 0 and get a real number out. That's an undefined situation. So this really takes care of the two problems that we have. Number one, well, we can't deal with imaginaries. Number two, we can't deal with undefined numbers in functions to graph them. Now, that does determine some things about graphs, but there's not going to be a point there that we can get out. And that's what that's really the point, is that what is your output for all of these numbers? Well, there's going to be some numbers where we don't have an output that's a real number, or don't have an output that's even defined. It's going to create a vertical asymptote for us when we get to graphing a little bit later. And I told you I was going to talk about graphing a lot. So when this happens, when your denominator is equal to 0 for some numbers, it's going to create this thing called a vertical asymptote. In logarithms and square roots, it just says you can't even get a number out. It's not that it's undefined. It's not even valid for this function. So that's a different story, and it's why we handle them different. Again, square roots tell you what you want to have. You want numbers that are positive. So do logarithms, actually. With denominators, you go, I just can't have this equal to 0. So when we approach it, we think about it like, well, do I care if the numerator is 0? You know what? If the numerator is 0, what that actually means is that's where if we have any x-intercepts, it's going to appear there. Where your numerator equals 0 is your x-intercepts. Your domain, on the other hand, is really only one problem for fractions if your denominator equals 0. So how we approach it, we look at it and go, you know what? I'm going to have problems. If I set my denominator equal to 0, that's going to be a problem. The one problem we can even have is if t cubed minus 16t actually ends up being equal to 0. So we're going to set this equal to 0, understanding something about it. That the numbers I get here are bad numbers. They're numbers that I cannot use. They're numbers that will be outside the domain because they're going to create a 0 on the bottom sort of idea. That's an undefined value for an output. So we can't include them, and we'll deal with that in the domain right now. So let's solve it. Remember, we're kind of reviewing what you can do. Whenever you have a power 2, power 3 expression that's equal to some number, so some equation here, you might try to factor it. So factoring says put your polynomial in order, and it is. Our exponents are descending. Factor out a GCF. So think about a number and or a variable that divides all of your terms, like t. T divides both of these terms. And we factor that out. All right, well, and then you keep going. Factoring is not like a one and done sort of thing. So we factor out the t, no problem. We have this, can you factor t squared minus some number? The answer is always yes. I know that you were taught that you can only factor these if that is a perfect square. And that's not true. If this number is a perfect square, it does make it easier, and that you can factor this as t minus 4, the square root of 16, and t plus 4, the square root of 16, and that's true. But if that number is not 16, some people will take this and say, I cannot factor that, and that's not true in this class. So typically when I teach like an intermediate algebra, the class before this, I'll tell them that this is possible. It's just that we probably have not covered square roots at that point. Once you covered square roots, we need to understand that this can represent that t squared minus 5, because if you square the square root of 5, you're going to get 5. Well, then if that's the case, then we can factor it. And that's perfectly acceptable in this class. So if you have t squared minus some real number, you're going to factor that. Moving on. So once we got this down, so we looked at this, we said there's no square roots, that's great. So, but I'm not thinking positive. I'm thinking, I know that with fractions, my denominator cannot be 0. So I'm setting it equal to 0, understanding that what I get out of this are numbers that I'm going to exclude, because those numbers, these 1, 2, 3 values that are going to give us 0 on the denominator, they're bad numbers for our domain, in that I will not be able to get a real number output. So using that zero product property, it says you got 3 factors, they're equal to 0. If any one of these factors equals 0, it's going to create a true statement in that equation. So t equals 0, no problem. T is 0, and then if either these are, I don't even care, 0 times whatever is going to give us 0. If t minus 4 equals 0, or in other words, if t equals 4, this factor is 0, I don't care what these are, because 0 times any other 2 real numbers is going to give us 0. And lastly, for the same reason, t equals negative 4. These things right here, and you see it, if I let these t values be evaluated in that function, then this is going to be some number, either 0 or 20 or negative 20. But for each of those 3 values, my denominator is going to be 0. That is not okay. We can never divide a number by 0. Even 0 over 0 is an undefined value. What that means is that you're going to have a hole in your function. And that's going to be like 30 videos from now. No, maybe 20 videos from now. That when we get a 0 over 0 idea, it's factorable and cancelable, you're going to get a hole. So your function is going to be going along. It's going to get a hole and then continue. That's what that number does for you. The other 2 numbers, these numbers, you can't plug in any of them. You can't have a 0. That's a bad number. Denominator is 0. Got to kick that one out. If t equals 4 or negative 4, your numerator is going to be some either positive or negative real number, and your denominator is going to be 0. That creates what's called a vertical asymptote. What in the world is a vertical asymptote? A vertical asymptote happens when you have this wall, like a force field, and your function goes up to it and says, oh, I can't cross it. I can't touch it. It's like MC Hammer, man. Do. Can't touch this. That's what that vertical asymptote does. It says your function cannot cross that. Why? Why? Because at that value, your function is not even defined. There is no point at the value t equals 4, and likewise at the value t equals negative 4. Now, I don't know whether it's going to go to positive infinity or negative infinity, but it's going to go to one of them. That's what these values do. I know that's a lot of stuff in a short amount of time, but there's so much to learn about our domain. Most of the time, we just figure out a process and we go with it and we never really get it. And then later on, it really kicks our butt, because you'll get into some other stuff where domain's extremely important. And frankly, it kind of hasn't been until we get to like this level and further. In calculus, domain is incredibly important. what you can and what you can't plug in, because sometimes we get answers, and if we assume the domain's all real numbers, we're going to be very, very wrong. So I'm going to give you a little recap to make sure that we're okay. Even though it might seem a little basic right now, it's super important to understand these two issues very, very well. So number one, domain is a set of inputs that for now, because we're talking about real numbers, must give us a real number output. That means square roots, because they have the potential to give us imaginary numbers, are a problem area for us to look at. And denominators, because they have the potential to create an undefined undefined number value, are a problem for us to look at. Notice, cube roots are fine. You can have negatives in cube roots, or fifth roots, or seventh roots, or odd roots. Even roots, like square roots, fourth roots, sixth roots, those are all going to have that same issue. Those will be problems. We're going to have domain issues there. Now, there's a difference between square roots and denominators. Square roots, we solve these domains, or we find these domains by letting this be greater than or equal to 0, because we think about it, a square root needs to be this. It needs to be greater than or equal to 0. Notice the needs to be. It wants to be this. This is the definition of what makes a square root work over real numbers, is set it greater than or equal to 0. It's going to give you an interval of numbers that is going to work for you. That's going to create the inside positive. That's going to give you a real number result, output. Denominators are backwards. Denominators aren't given by what you want to have. It's given by what you can't be. So with a denominator, it can't be 0. So we set equal to 0 and solve it down and say, these things are not okay. If I let those happen, I'm going to get some bad situations for us as far as the domain. Now, graphically, they do help us. So we use this to graph. I already told you that's going to be a hole. Those two are going to be asymptotes. If you have 0 over 0, that's a hole. A little removable discontinuity, something that's just a missing point. These two things are vertical asymptotes, and we're going to learn a lot about it. But as far as domain is concerned, those are problems that we must exclude. Notice, this says what I can have, what I must have to make it work. This says what I must not have to make it work. Do not confuse the two. So for our domain, we can say x, not x. Why is that wrong? Why is x wrong? Remember that this first thing in set builder notation is an independent variable. So if my variable changes, I need to change that and say, look for t's. Okay, what can t be? T can be all real numbers except, or but, or and then we list our exclusions, and we say, we've got to exclude some values because they're going to create some undefined results for us. That's t equals 0, and t equals -4, and t equals +4. Those three numbers are the only numbers in the world. Power 3 says we're going to have at most 3 results. Power 3 says these 3 numbers are the only numbers in the world that they're going to create a denominator equals 0, and therefore an undefined result for us in this function. It doesn't matter about positive or negative. It's a fraction. They can be positive or negative. Don't confuse a square root with the denominator idea. How we do this with interval notation it's fairly ugly. You see, when you exclude one number, how we do that in math, how we do that with interval notation, is we say all real numbers would be this. Check it out. All real numbers would be that. That's all real numbers, from negative infinity to positive infinity, no problem. If we want to exclude values from that, then we're going to insert 4 little exclusions. Well, how do we do it? We insert an exclusion by putting this in order and saying, you know what, I can go from negative infinity all the way up to -4, but parentheses exclude values. Brackets include them, parentheses exclude them. So this would be like -4.00000000000 for a long way, and then a little 1, and then say, yeah, but -4 is not included. And then we'd start up again at -4, but a little bit more than that. So this says, hey, go from negative infinity up to -4, but just before you get there. Now, just after you've left -4, and that's what excludes this point, -4. Then you can go all the way up to 0. Notice it's in order. But you've got to exclude the 0, and then you can go up to 4. But then you've got to exclude the 4, but then you can continue on. Square roots give you an interval, says what you can't have. Denominators say, here's an interval, and it says what you can't have. It's done two different ways. That's got to make sense before we go on any further. So we need the idea of inputs as domain. We need the idea that it's the set of values that's giving you a real number output. And if you think about that, it really should just follow directly that square roots want to be positive because negatives give you imaginaries. Can't have those. It's got to follow that denominators can't be equal to 0 because if that happens, we get something that's undefined. We're going to come back with just a couple examples. It's going to be pretty quick. Going through and exploring these ideas a little more. Remember that later on we're going to add one more scenario to this for this class, and that's logarithms. Logarithms fall into the same category as square roots in that the inside, the argument, wants to be positive. So if you're dealing with that right now, all we need to do with the inside of a logarithm is set it greater than 0. It can't even equal 0. So logarithms, the inside has to be positive because of the way it comes from an exponential. When I take a number to an exponent, a positive number to an exponent, I always get, we always get positive numbers out of that. And since our basis for exponentials are positive, our output for exponentials has to be positive, and therefore input for logarithms, since their inverses, have to also be positive. So that's the other domain issue. We deal with it much later, and I'll explain it thoroughly when we get there. So I'll come back in a little bit with 2 examples. Okay, so I lied. I said 2. I meant 3 examples, because I really want to deal with that one too. We just talked a long time about what inputs are as far as the domain, and that these inputs need to give you a real number output for your function. And if that doesn't happen, well then you got to exclude them somehow, or tell the domain what it has to have in order to make this function work for you. And we looked at 2 problem areas. We looked at square roots and denominators. And I said, there's going to be another one, logarithms. I'm going to kind of hide it for now. We'll talk about it later when we get to logarithms and really, really explore those. So what happens if your function doesn't have square roots, and it doesn't have denominators, and it doesn't have logarithms in it? Well, then your domain is all real numbers for every polynomial that you have. Every polynomial, that's things without square roots. That's things without fractional exponents that are radicals, like square roots. That's things without fractions where you have a variable on the denominator. Notice I don't mean fractions like this. Fractional coefficients like 3/5, that is not what we're talking about. We're talking about fractions where you have variables on the denominator. You don't have square roots, you don't have fractions on the denominator, where variables on the denominator, you don't have logarithms. Your domain is going to be any real number, all real numbers. So if you look at this and go, hey, no fractions at all, no square roots, no logarithms, your domain's all real numbers. So how do we write that? We can say x such that x is a real number, or x such that x is all real numbers, or x such that x is, you can use a block letter R for all real numbers. Or we can say interval notation, negative infinity to positive infinity. That's another way that we can say all real numbers. And what that says is plug in anything, you're going to get a real number out. And that's true for that function. If we move on to something like this, though, man, that's nasty. There's a lot of stuff going on there. Don't be confused when you see both fractions and square roots. What we deal with here is each of those issues independently. So you don't have to put them all together. We're going to on that one. I'll show you. It's a nice little trick we can use, but you don't have to do that. We can think, okay, well, I have a denominator and I have a square root. Let's think through both of those. So let's do the denominator first. What do you know about denominators? Well, we know that denominators equaling 0 is a bad thing for us. I could put in any number here for the denominator as far as the denominator is concerned, as long as it does not equal 0. So when we do this, when we see a denominator, it's telling you there's numbers that I can't be, okay? So there's numbers that I'm plugging in here that might be issues. So we're going to set this equal to 0 with the understanding that it's a denominator. If it equals 0, I'm going to have problems. So when you add 4 and say, hey, that number 4 obviously is going to create a 0 on the denominator. I don't even care what's on the numerator right now. if this function, if we allow this function to have x equals 4 as an input, we're going to have an issue right here. That's a problem issue, so we say we must exclude 4. So setting the denominator equal to 0, not greater than or equal to 0, says you're going to have some bad numbers here, or numbers that you can't have in your domain. And that one of those numbers is 4. Now we look at our square root and we understand that something's switching. We're not worried about 0 so much, we're worried about keeping it positive because we need real numbers. Oh yeah, real defined numbers. This would create an undefined number. Let's think about here. I need values of x that keep this part of my square root greater than or equal to 0, that keep it positive or 0. Well, what's that going to be? We solve it, it's going to give us a range of numbers, some interval that's going to keep the inside of my square root positive, and that's what I need to have happen to get a real number out of that square root. So if we add 15, we do not switch the inequality ever when we're adding or subtracting. And divide by 3, we do not switch the inequality unless we divide by a negative. This says that as long as you have numbers greater than or equal to 5, you're going to keep the inside positive. As long as you keep the inside positive, you're going to get real numbers out of that square root, and that's what we need. Do you see the difference between how we treat denominators and how we treat square roots? You've got to see the difference. One is about keeping it positive so that you get a real number. The other one, the denominator, is about not letting it equal 0 so you don't get something undefined. And understanding that we need real numbers out that are defined is how we approach dealing with square roots and those fractions. Now, we will put this in the domain and say, all right, set builder notation, x such that, and we're going to put both these up there, right? X needs to be greater than or equal to 5, and x cannot equal 4. And then we're done. And your teacher's probably going to go, think about this for a second. And not that you're wrong, all right? Not that you're wrong, but that it's redundant. Look at how this says x needs to be greater than 5, and look at how that says x can't be 4. And you go, all right, so we know, right? We know that this has to happen. We have to have that in order for this to even give us real numbers. But then it goes, oh yes, but make sure you don't get a 4 in there. Isn't this already excluding the 4? So our x says, you gotta be more than 5. And then I said, yeah, but make sure you don't get a 4. Well, that's a redundant thing. So we really would not have this x is not equal to 4 for this scenario. We don't need it. That's a redundant. Now, I'm going to play around for a little bit. What would happen? What would happen if, you know what, I'll do this too. Our interval notation would be, here's 5, here's greater than that. So we'd go from 5 to infinity, parentheses on the infinity, a bracket on the 5, because we can actually equal that value. So this would be our two domains for this scenario. Now let's play around. What if I made this not 15, but 12? Well, that's not right. If we end with, hey, in order to make that square root positive, you need numbers bigger than or equal to 4. All right, I need numbers bigger than or equal to 4. Is this now relevant? Absolutely, because this says I need numbers that are greater than or equal to 4, and this one says you can't equal 4. Now, instead of writing this, it's a little bit easier to write these together. If we say that x has to be greater than or equal to 4, and this one says x can't be 4, then this is one way to say it, but maybe more importantly, or more appropriately, we can say, what if we just exclude that equal sign? That says that x has to be greater than or equal to 4, but not equal to 4. It just takes out that equals part of it. And so what we get here is this domain. So x must be more than 4. Or, using a parentheses, x must be more than 4 can be written in interval notation just like that. Okay, last iteration of this. Let's change this to 9. So 9, 9, 9, 3, 3, 3. What now? Is this one relevant? Yeah, absolutely. This says you need numbers that are greater than or equal to 3 to keep this thing happy. And since 4 is now in that interval, you need to express it separately and say, I also can't have 4. That makes sense. Say, hey, you know what? You need numbers more than 3, at least equal to 3, but make sure you exclude 4 because that number is going to make this denominator not work for you. That's what's happening here. On interval notation, it's pretty awkward to show with interval notation. We would say we do this because 4 is up here, right? 4 is this problem. So we'd start at 3 with a bracket. You can include the 3 and you need to. We'd go up to 4. We'd say, you know what? You need to exclude that 4, but then after that, you can keep going forever. That's how we'd write that for interval notation. Man, I hope this makes sense. I hope you're seeing the ideas behind domain really producing fruit for you. Understanding real numbers here mean positive. Defined numbers here mean not 0, and that is how we approach find a domain. The last one, I'm going to go through it very quickly. Obviously, we have a fraction. We also have some square root. So let's really think about it. There's two issues, right? We know that the denominator has a square root in it. We know that square roots want to be positive. So when we write this, you go, let's talk about the square root first. Let's understand that in order for us to get real numbers, I would have to have x minus 8 being greater than or equal to 0. That's the square root idea. Just the square root idea says keep me positive or at least 0. So I want this to happen so that this guy's happy and gives me non-imaginary numbers, gives me real numbers. But it's on the denominator. Denominators say, I get that you want to be greater than or equal to 0 because you're square root, I get that. But remember, denominators are not happy if they equal 0. So what if we just don't include the 0 part of it? Now we've excluded the only value that can possibly make that 0, and it would be 8. So 8 minus 8 is 0. The square root of 0 is 0. So if we exclude the 8, if we exclude that idea that, hey, I can be equal to 0 here, then we're excluding the only number that's going to let that denominator be 0. So we kind of put these ideas together sometimes and say, cool, but we know what? We can't have that actually equal 0. So we're just going to take that away from that inequality. If we add 8, nothing changes as far as reversing inequality. We get x is greater than 8. That's our domain. We can set this up with set builder notation. We can say, hey, x is positive and more than 8, but it can't include the 8. So our interval notation says, let's start at 8 with a parentheses. We cannot include it because that would make 0 on the denominator fraction, and we go to infinity. I hope that this has made sense. There's only one more thing that I want to touch on. Sometimes you'll get some fractions like, let's say 5 over x squared plus 1. And you go, all right, great. Can that denominator, let's think through it. Does it have any of the problem areas that we know could cause issues for us? Well, it doesn't have any square roots. It does have a denominator. And so you go through the process and you go, you know what? I know that if denominators equal 0, I've got problems. But then you think about it and go, can that actually equal 0? And the answer is no. Not over real numbers, and that is what we're talking about. So if I take any number in the world that's a real number, and I square it, which gives me a positive, or at least 0, and then I add 1 to it, there's no way it's going to equal 0. That's impossible. Positive numbers plus 1 can't equal 0. And so this says there's no solution to that, no real number solution. That's fine. What that means is if there's no real solution that's going to make your denominator equal 0, then there's no problem. There's no domain problem here. Your domain would be all real numbers for that. Even here, if I take a square root of that, you go, oh man, I know square roots have to be positive. So you think about this one and say, all right, the square root of x squared plus 1 has to be greater than 0. Not equal to 0 because it's on the bottom of a fraction. You go, well, what numbers are going to make this greater? I can't even solve that. Oh, geez, what do I do? Well, if you square a number and add 1, is it always positive? Is it ever negative? It's never negative. It always has to be positive or real numbers. That's also telling you the domain's all real numbers. So sometimes we really just have to sit there and think about it a little bit and understand the ideas behind the square root and the denominator. If you have something that cannot equal 0 on the bottom of your fraction, your domain's all real numbers. If you have something in a square root that cannot be negative ever, no matter what you plug in, then your domain is all real numbers. So I hope that you'll get this from time to time. I hope that makes sense to you. I hope also you understood my comment about with fractions, we're really only concerned where your denominator has variables in it. So like x minus 2 over 4, that 4 is a constant. It can never equal 0 on its own. So your domain here would also be all real numbers. We're going to stop there. We've explained what domain is again. We've talked about how to find it with square roots and with denominators and the interplay between those. Later on we'll talk about logarithms. I hope it makes sense. And we're going to come back in a little while with how to find operations of functions and their domains. So I'll see you for the next video on that.